Hello, my name is Rusty Oliver. I'm standing in the Combat Robotics Armor Test environment. I wanted to take a moment to point out a detail that was shown in our last video. Two shock mount assemblies. These are stainless steel. They don't look like they would be particularly rigid. The idea is that we want this to be able to move somewhat flexibly, and these will handle the compression and the shock load. They look as though they would not be particularly stiff, as though they wouldn't be something that would actually absorb a lot of movement. But in fact, there's just a lot of, I'm leaning into the frame and pushing with as much as I've got, and there's absolutely no movement. So when we saw the movement that we did in the last video, which was significant, we're actually talking about a lot more force, a lot more kinetic energy than one might readily assume. All of the weapons in BattleBots use kinetic energy to affect the opponent. So as we're testing the armor, we need to know how much kinetic energy is actually being absorbed by the armor and how much is imparted by the blow off of the weapon. So Zoe's going to walk us through the analysis and math.
Hi. Yeah. So in BattleBots, kinetic energy transfer is the name of the game. And kinetic energy equals 1/2 moment of inertia times rotational velocity squared. Moment of inertia is a property of materials that has to do with the mass of the object, but also the distance of that mass from the axis of rotation. We know the rotational velocity of the blade because we have the tachometer readings. The moment of inertia doesn't change during a hit, but the speed drops dramatically. If we take the initial rotational velocity, put it into that equation, and then we take the final rotational velocity, put it into that equation, and subtract those two, we'll know how big of a hit Tomb Clone put on whatever we're feeding it.
We have a CAD model of the weapon in Fusion 360. It calculates the moment of inertia at 2.45 kilogram-meters squared. In the hit on the server, the RPMs dropped from about 1600 to about 1400 RPMs. When we plug the numbers in, we get the result that the blade's kinetic energy dropped by about 7,900 joules, or 7.9 kilojoules.
John Deere lawnmower. Served me well for many years, mowing at half an acre many times during the summer. Last weekend it seized up on me. Lawn care is a lot like life. As long as you're useful and do your job, there's a place for you. If you can't do that, there's consequences.
3, 2, 1, go. 3, 2, 1, go. Ooh. That's it? Oh.
We've learned a couple of things about the approach speed and how that's going to affect the amount of impact that these receive. Because it's all over the map. This one took a really good hit, as did this one. And this seemed to go in at the correct speed, but it hit at such an angle that it just kind of deflected it. So we can see that there's a ton of force from the impact. This is all kind of smeared. It's almost galling, and then ripping this out. Most awkward load ever. Should work. So I'll just grab a couple little sticks of steel. Up there. My work here is done. What I just realized, welding is a really quick procedure. It's something you can do very quickly. And I just now realized that the last time we fed the lawnmower into the crate, we barely had enough room to sneak it through. And so I have just welded it up in a way where it absolutely will not fit through the opening that we have. So what I'm going to do is make an adapter by cutting it right here through each of the 3 supports. I'll weld a washer on the end, and then we can bolt laterally through the washer, and that will work well enough for what we're doing right now. We flipped it upside down, took the gas can off of it, and put it up on some temporary supports so that it's presenting the bulk of the mass of the item to the blade. And so we should see a more robust hit, we should see a greater drop in the RPM here, and that will give us a good sense of how much impact this system actually sustained. So we expect this to be spectacular, and we look forward to sharing it with you. I think we all know how this ends.
Are you the lawnmower man?
Not today. Tucked a lawnmower into a large blade that looks like the god of lawnmowers. Let's see what happened. There's a lot more shrapnel and debris in here and even smoke. So it looks like this is where it took the bulk of the impact. This is all fresh, tore that. There's another impact here. These were straight-ish recently, and now they are not.
That plate was flat, right?
That plate was completely flat. It is not flat anymore. That's, I think, 3/16 mild steel. Yes. So there's basically no movement on the blade. So this sustained an impact without actually deforming along this edge at all. Yasha trued it up before we sent it, so like nothing really happened here. So that's interesting. Our sled. Our poor sled. This is cleaved, or that's directly through the material. That's just amazing. So these are welds that were at least competent. I made them, so I'm pretty confident in them. This broke the weld. This is obviously a pretty serious hit. It bent this along the most substantial axis, which is this axis. So it bent a piece of about 3/16 mild steel channel into just a taco. This was ER70S6, so the weld material is good for about 70,000 pounds tensile, so it's a substantial electrode, and this is the one that really alarms me, I guess, because this hit in such a way that it just took the blade straight through the material. So we know that the blade here is substantially harder than this. We knew that already. But this type of impact is just, it's impressive because it took it all the way through the main axis here and snapped the tacks on the other side and ate part of the way into what was probably a grade 5 or grade 8 bolt.